In the previous lecture, we have seen the basic introduction, or you can say a brief introduction of general theory of relativity. In fact, we have discussed why general theory of relativity was needed, what was the limitation of Newtonian mechanics and the special theory of relativity, why the concept of space-time was changed. All these things we have seen in our first lecture, which was just an introduction regarding this general relativity. Okay. Now, today we are going to see a very important principle of general relativity. This is called the principle of general covariance. In fact, what is this principle of general covariance and how we can explain it? All these things we will learn in this short video. In your examination, this question will be definitely asked in short answer type question. For writing a short note or give the brief explanation of principle of general covariance, such type of question will be asked in your examination. Okay. In fact, this principle of general covariance is the foundational concept of Einstein's general theory of relativity. This provides the foundation stone, you can say, to the general relativity. In fact, you know that a special theory of relativity is limited only for inertial systems. And that's why its name is a special theory, because this theory is not valid in a non-inertial frame. Or you can say this theory does not comprise gravity or gravitational force. Because whenever you talk about a physical law in the presence of gravitational force or gravitational field, the frame will be accelerated. And in accelerated frame or in presence of gravitational field, the special theory of relativity is not valid, as you have seen in our first introductory lecture. So we simply say that Einstein's special relativity is limited only to the inertial system. Okay. So, in fact, you have, when I studied the special relativity, I have provided a complete playlist on special relativity. You can watch my video on special relativity, which almost contains 23 to 25 videos or almost 30 videos. Okay. Then you have definitely studied the postulates of special relativity. There are two postulates of special relativity on which this theory is based upon. And the first postulate of special relativity is called principle of relativity. And in that first postulate, that is principle of relativity, you have definitely studied that all laws of physics, or you can say all laws of nature, are covariant under the transformation of inertial frame. It means you can also say that according to the principle of special relativity, the laws of nature retain same form in all inertial system. When you move from one inertial system or one inertial frame to another, the form of physical laws do not change. This is the first postulate of special relativity. Okay. So you can see that this postulate actually limits special relativity only to the inertial system. Okay. But what will happen if you want to generalize this principle for all coordinate system, that is both inertial and non-inertial. In fact, this problem was felt by Einstein himself, and Einstein realized that gravity could be viewed as a manifestation of curved spacetime and thus needed a new framework, a framework where no coordinate system is privileged. It means our physical laws must be expressed in a particular form or in a covariant form that will retain its mathematical form in all inertial frames. Not only in inertial frame, but in all frames, that is both inertial and non-inertial frames. Okay? So you can say that if our aim is to generalize the principle of special relativity for all coordinate system, that is for inertial as well as non-inertial system, definitely we have simply to remove this word inertial. As this postulate says, the laws of nature retain same form in all inertial frame. So if you remove this word inertial, then this statement will be the laws of nature retain the same form in all systems, all frames. Okay? That will be called actually the general covariance principle. Here covariance principle is not general, it is limited to inertial system, but if you generalize this principle to both inertial and non-inertial system, then it will be called principle of general covariance. Okay? So the principle of general covariance of relativity may be stated in this manner. You can say the laws of nature retain their same form in all coordinate systems, or you can say in all frames. When you say in all frames, that means you are talking about both inertial and non-inertial frames. Okay? In other words, you can also say that the laws of nature remain covariant independent of the frame of reference. Okay? Frame of reference, that is inertial frame or non-inertial frame, will change. We will move from one coordinate system to another. But the mathematical form of our physical laws or the natural laws will not change. Actually, this basic principle is known as the principle of general covariance. Okay? Now let us try to formulate this general covariance principle in mathematical form. So how we can mathematically formulate this principle, let us see. In fact, according to this principle, we must express all the physical laws or natural laws by means of equations in the covariant form, which are independent of the coordinate system. If you are successful in casting the mathematical form of natural laws in such a form which is covariant under the transformation of frame, it means frame will be transformed from one to another. Let us say one is S frame with the coordinates, let us say xi, and another is S prime frame with the coordinate xi prime, and you move from this S frame to S dash frame, but the form of our physical law is such that it does not change. Okay? So definitely for the validity of this principle, we must have to write physical laws in a particular covariant form, so that whenever there will be a transformation of frame, the form of physical laws will not change. But what is the mathematical, what should be that mathematical form? If you have studied tensor, as I have told you earlier, that tensor is, the knowledge of tensor is indispensable for the study of general relativity, because the strong mathematical tool which will be always needed to explain general relativity, that is tensor analysis. So you must have a concrete knowledge of tensor. I have provided a playlist mathematical physics in my channel, where you will get some videos on the basic algebraic operations of tensor. And so I will suggest you go through all those videos so that you have a basic knowledge of tensor analysis. But after that, you will also need the concept of tensor calculus. And I will actually provide some of the videos on the important concept of tensor calculus, and also some of the videos on some tensors which are of fundamental importance here. Actually, if you have an idea of tensor, then you will see that actually the tensor equations are covariant, because tensors are quantities which are same in all reference frame. Therefore, if your aim is to cast a physical law in covariant form, definitely you have to express the laws of nature in the form of tensor equations. Okay? Because tensorial equations have a very important property, that they are covariant under frame transformation. Okay? So I have mentioned that as the tensor equation has exactly the same form in all coordinate system, so we must express all the natural laws in tensorial form. Okay? And whenever you will express, or when you will cast the physical laws or natural laws in tensorial form, they will be, that is called covariant form. And the mathematical form of that very equation will never change. It means in every frame, either inertial or non-inertial, the form of the law will remain same. Okay? Now I will try to illustrate this statement, or this principle of general covariance, by some important examples. Although first example I am giving you, which is actually Einstein's field equations. In the general relativity is actually based on this Einstein's field equation. And I hope you have not studied this Einstein field equation till now, but in our forthcoming videos, we will explain this Einstein's field equation in very detail. But here, just for an example, I am citing this equation. Just you have to remember this, but the complete explanation of Einstein's field equation we will learn in our forthcoming video. In fact, you can write the Einstein's field equations in general relativity in this manner. G mu nu equal to 8 pi g over c to the power 4 times t mu nu. Actually, you know, here G mu nu, this is a covariant tensor of second rank. Okay? And this tensor is called Einstein's tensor. Okay? And in RHS, the tensor T mu nu, you can also see this is also a tensor of second rank, and it is a covariant tensor of second rank. In fact, this T mu nu, this is called energy momentum tensor. Okay? And you know, G is universal gravitational constant and c is the speed of light in free space. As you can see, this equation is in tensorial form, because in LHS there is a tensor which is called Einstein's field Einstein's tensor, which is a second rank covariant tensor. Okay? And the RHS of this equation also contains a second rank tensor T mu nu, which is actually energy momentum tensor. Since both sides of this equation contains the tensor of second rank, therefore this equation is in covariant form. If you will write this equation in a coordinate system with the coordinate x, then this will be the form of the equation. And if you will write this equation again in another frame, let us say with the variables x dashed, the form of the equation will not change. In that very equation, you will see that g prime mu nu will be equal to 8 pi g over c to the power 4 t prime mu nu. Here, this primed quantities actually represent the Einstein tensor and the energy momentum tensor in this primed coordinate system. And that primed coordinate system actually may be a inertial system or a non-inertial system. Okay? So this is actually in covariant form. Okay? Now, for a second example, you can take, I have actually written this example in my introductory lecture on general relativity. You know, the tensorial form of line element is given by ds square equal to g mu nu times dx mu times dx nu, where this mu and nu are equal to 1, 2, 3 and 4. Actually, this will be dx1, dx1 and dx2, dx2 in this manner. Okay. Here, this g mu nu is what? This is, you know, this is called metric tensor. This is in fact the fundamental covariant tensor of second rank. Okay. And due to the presence of this tensor quantity g mu nu, you can say that this is the tensor form of the line element. In Minkowski's four-dimensional space, if you want to write the expression for this line element, then you write it in this manner: ds square equal to dx square plus dy square plus dz square and minus c square dt square. This is not tensorial form. But when you write this expression in this manner, that is ds square equal to g mu nu dx nu, this is actually called the tensor form of the line element. And this equation, you will see later on, will have same form in every coordinate system. Okay? Because it has been written in tensor form. How we can say that this will be in same form in all coordinate system? Because you know that this quantity g mu nu, which is the metric tensor, or you can say a covariant tensor of second rank, this obeys the transformation law like this. Actually, such transformation law I have already discussed in very detail in the chapter Tensor Analysis in my playlist Mathematical Physics, you can see. Here, G mu nu is the metric tensor in the frame unprimed coordinate system, that is the coordinate system having coordinates x. And G prime ij, these are the components of the metric tensor in the primed coordinate system. And if you know the components of the metric tensor in unprimed coordinate system x, then you can find its components in the primed coordinate system by this transformation law. That is G prime ij equal to G mu nu times del x prime I over del x mu times del x prime j over del x nu. Okay. So, as I have told you, the prime quantities correspond to the new coordinate system. Okay. So, this equation will have also same form in the prime coordinate system and also in the unprimed coordinate system. Okay. Now, actually, to prove this statement that the laws of nature have the same form in all coordinate system. Okay. Let us now take a concrete example so that we can say that if a natural law is expressed in the terms of tensor equation, then it will have same form in all coordinate system. And for explaining this very fact, let us consider a certain law of nature in the system of variables x, and this law is represented by this tensor equation. I have written here a superscript mu and subscript nu, a mu nu. You know, this is a mixed tensor, and that is equal to the mixed tensor b mu nu. This is the tensor form of a physical law. Let us consider. And this law has been written in unprimed coordinate system. Okay. Now, you can see that actually when a mu nu is equal to b mu nu, it means this law has been written in the unprimed coordinate system. If you will write this particular law in the prime coordinate system, the form of the law will not change. It means we can say that a prime mu nu will be equal to b prime mu nu. But how you can prove this? Let us see. For this, actually, we will see that transformation equation for both of these tensors. Both are mixed tensor of second rank, you can see. And if you consider that the components of the first tensor in the prime coordinate system is a prime mu nu, and that of the another mixed tensor is b prime mu nu, then a prime mu nu minus b prime mu nu, what will be this? You know, if in unprimed coordinate system the components of this tensor are aij, then a prime mu nu can be written as del x prime mu by del xi times del xj by del x prime nu times aij. Okay, and minus this b prime mu nu, this can be written as bij times del x prime mu by del xi minus del xj by del x prime nu. Now you can see, you can take this factor common. Okay. And so after taking this as a common factor, our result will be aij minus bij times del x prime by del xi times del xj by del x prime nu. But you have seen, I have stated here in this equation 3 that in the unprimed coordinate system, both of these quantities are equal. So what is this aij and what is this bij? These are the tensors in the unprimed coordinate system. But as our equation 3 says that a mu nu is equal to b mu nu, on this basis you can say that aij is equal to bij. And if aij is equal to bij, then this will be equal to 0, and therefore you can say that a prime mu nu minus b prime mu nu, that's equal 0. And therefore you can say that a prime mu nu is equal to b prime mu nu. So what you are seeing here, Actually, you can see in this equation 4 is exactly the same form as that of this equation defined in 3. Okay? So you can say the laws of nature, when expressed in the form of tensor equations, follow the general covariance principle. It means the form of the mathematical form of any physical law does not change due to the change of reference frame. Not only inertial, but either inertial or non-inertial. If you will move from inertial frame to non-inertial, even after that, the form of the law will not change if you are able to express that law in covariant form. Covariant form means tensor form. When you express a physical law in tensorial form, that is called the covariant form. Okay? So you can say that the general covariance principle, according to this general covariance principle, the laws of nature must be expressed in the form of tensorial equations. Okay? So you can see how important is the concept of tensor for the study of general relativity. Because this basic principle of general covariance is the foundation of general relativity. And for the validity of this principle, definitely you have to express any physical law in tensorial form. Okay? So you must have a concrete knowledge of tensor analysis for the study of this general relativity. Okay? Now, actually, as I have told you that this question in your examination is basically asked as a short answer type question. If you have to write a short note, or if a question is asked in this manner that briefly explain the principle of general covariance, then you may end your answer up to this. From beginning of this video, you can end your answer at this point. But in this present lecture, I will talk something more for your knowledge regarding this principle of general covariance. Okay? If you have a sufficient time in your examination, you can write these things also, but this is not necessary for writing your answer in your examination. Okay? So after knowing the principle of general covariance, now you can see what is the philosophical significance of this very principle. In fact, I have mentioned here two very important philosophical significance of this principle. In the first significance, I have mentioned that general covariance reflects the idea that the geometry of space-time is not absolute. Mark it. This general covariance principle gives the idea that the geometry of space-time is not absolute, but it's shaped by the distribution of matter and energy. How the matter and energy are distributed, that determines, that decides what will be the shape of the space-time, what will be the geometry of the space-time. Okay? This is a very remarkable fact. Geometry of a space-time is not fixed. It is governed in accordance with the distribution of matter and energy in space. Okay? This is a very remarkable philosophical fact. Now, another significance of this principle, you can say, it shifts physics from background-dependent theory like Newtonian space and time to background-independent framework. You know, the Newtonian theory, also the Einstein's special relativity, these are background-dependent theory. Why these are called background dependent theory? Because these are actually limited only to the inertial system. These do not provide the general theory. But when you talk about the principle of general covariance, then we express the physical laws in such a tensorial form that is valid, that retains its form in all coordinate system. So here the frame of reference does not matter. So we say that this principle shifts physics from background dependent theory to background independent framework. Okay? So these are the two very important philosophical significances of this principle of general covariance. Okay? Now, after knowing the concrete idea of principle of general covariance, let us see three very remarkable facts regarding this general covariance. In first remarkable fact I have mentioned, you can see, arbitrary coordinate transformations obviously include a subset of transformations that take us locally from non-inertial to inertial frames. Okay? In the inertial frame, gravitational forces are absent. Gravitational forces are present only in a non-inertial frame, not in inertial frame. Okay? So, if you now consider generally a covariant equation, okay, then it is either true in every frame or false in every frame. If it is known to be true in locally inertial frames, that is in the absence of gravitation, then clearly it is true in every frame. If a law is true in absence of gravity, that is in inertial frame, it will be also true in non-inertial frame. Okay? In other words, you can say that the equation, if the equation is true in the presence of gravitation, okay, those equations which were actually true in absence of gravitation, that will be also true in the presence of gravitation. But why? Because gravitational forces are present in the non-inertial frame. Okay? That's why we now simply say that if you find that a law is true, a law is correct in an inertial frame, it will be valid, it will be correct also in non-inertial frame. Okay? Now, how we can actually cast an equation in covariant form? This is actually the basic or core problem of this covariance principle. In fact, the principle of general covariance gives you a precise prescription through which you can introduce gravitational forces into physical situation. If we know the equation describing the system in absence of gravitation, then you can write that equation in presence of gravitation on the basis of this general covariance principle. Because for the later equation, that is in absence of gravitation, we will take the laws of a special theory of relativity, because a special theory of relativity is successful in explaining the phenomenon, the laws in absence of gravitation. So if your aim is to write an equation in covariant form, you have to take the equation on the basis of a special theory of relativity. That is, you have to write the form of equation when gravity was absent. And once you write down the equations which has been actually written on the basis of a special theory of relativity, then you can write down the equations which will be valid in presence of gravitation, or you can say in non-inertial frame. And for this, what we will have to do? You have to take the corresponding equation of STR and then make them generally covariant. So taking the equation from special relativity and making them covariant, we can formulate the physical law in such a form that will be invariant or covariant in all reference frames. And as I have told you earlier, if your aim is to cast a mathematical law or a physical law in covariant form, what will be the mathematical apparatus? You know, you have already seen that mathematical apparatus is nothing, this will be simply the tensor. Okay, because you have seen that tensorial equation is actually covariant equations, because tensors are quantities or tensors are objects which are same in all coordinate system. So finally we come to the question of suitable mathematical apparatus through which the principle of general covariance can be implemented. And this apparatus is nothing, this is simply the general tensors. That is the tensors defined with respect to arbitrary coordinate transformations. And so in our forthcoming videos we will see some of the basic concept and the basic tensors in very detail. But regarding this principle of general covariance, there is some misinterpretations too. What are the important misinterpretation? How people misinterpret this principle of general covariance? Let us see. In fact, general covariance is necessary but not sufficient condition for general relativity. This is a very remarkable fact. For general relativity, this general covariance principle is necessary, but it is not sufficient. When you say that general covariance is necessary for general relativity, but it is not a sufficient condition for general relativity, what you actually mean? In fact, you will see many theories can be written in a generally covariant form, but that does not make them physically correct. So we simply say that this general covariance is necessary condition for general relativity, but not sufficient condition. It means if you cast a physical law in tensorial form or in covariant form, it is not sufficient. You can't say that that law will be actually definitely true. You can't say. Okay. In fact, in the beginning of the development of general theory of relativity, Einstein overemphasized its physical content. But later on, he felt and clarified its true role as a guiding principle for formulating gravitational law. This just acts like a guide. It does not work completely, but it will just give you a guideline, okay, for the gravitational laws. Okay. So I hope now, after knowing all these things, the idea about the principle of general covariance will be definitely clear to you. And so watch this video seriously and enjoy the lecture. Okay, thank you very much.